Kia ora koutou, no mai, haere mai. Welcome to lesson 34 for introductory physics. This lesson is going to take what we've seen about waves already, what we've learned about waves, and discuss some of those properties in relation to electromagnetic waves, which, as we've already established, are what we call light, but not just visible light, also X-rays, gamma rays, microwaves, radio waves, and so on. So that's what our goal is for today. Learning outcomes are to, first of all, explain what light is, state the different parts of the electromagnetic spectrum, explain the different outcomes for light meeting matter, and then we're going to look at refractive indexes, which is the speed of light in different mediums. So it travels at different speeds. We want to understand why that happens. We also want to look at shadows, which you're familiar with shadows, but we want to define a couple of terms around that. And then lastly, we're actually going to return to thermal physics, and we're going to look at thermal radiation curves and specifically the greenhouse effect. The textbook covered that section with the thermal physics section, but without an understanding of frequency and the types of electromagnetic wave that we're going to look at, I felt it was better to leave it until now than when we are looking at electromagnetic waves. So that's our goals. First of all, though, what is electromagnetic radiation? We've already met the idea of photons. I told you to just treat them as tiny little packets of energy, and we talked about hot things having a bit much energy, and so they give off some in terms of photons. In fact, everything in the universe that has any temperature above absolute zero, which is everything, gives off some of this thermal radiation, and photons was how they do that. They give off little photons, which are little packets of energy. We also talked about the idea of electrons jumping between electron levels on the atoms, and as they jump down, and so they need less energy, like releasing a spring, they're giving off some energy. As they jump down, they need to give off some energy, and that could be visible, it could be ultraviolet, but it can also lead into X-ray photons in the biggest electron jumps. And we also met in nuclear decay the idea of a nucleus giving off an alpha or beta particle, but also giving off a gamma photon, a really high energy photon, higher even than those X-ray ones. So we've already met these photons, we've already been talking about them and discussing them as though we sort of know what they are, but we haven't really said what they are yet. We've just said that they're little packets of energy. And that is true. A photon is just a little packet of energy, but they are actually a type of wave. It's a wave packet. So a wave packet is a term you don't really need to know. Just imagine the wave pulse we talked about for a rope, right? Imagine if instead of just one flick, you gave it maybe a half a dozen flicks. And so there was like a half a dozen little pulses traveling down the rope as a little lump. That's kind of like what a photon is, right? But it's a wave. And that means there must be some kind of medium, right? What's oscillating for the photon? So we know it's a wave packet, we know it's carrying energy because that's all a wave is, but what is actually doing that oscillating? It's clearly not a rope or matter because we know that the sun sends energy to Earth in the form of photons, and there's no matter or very little matter between the sun and Earth, so it can't be matter that's oscillating. So what is actually oscillating? Remember when we talked about electric fields, we had the idea of a charge creating an electric field. And if it was a single charge, then it just created straight lines radiating out, as per this little diagram on the left here. Just straight lines straight away from our positive charge. But let's say that we started to move that positive charge. Let's just move it upwards a little bit. As we move it up, then that field line that's coming out of our proton will move up with it, right? But the field line travels through space at the speed of light. The speed of light is how quickly that information travels. So as you move it up, the field line follows it up, but this bit down here is still down where it was a moment ago. And so then it's up here, and so the field line's up here, and then it moves back down, and then the field line moves back down. And so if you move that particle up and down, you can make the field line become a sine wave, right? And so that's exactly what the electric field is doing when an electric charge oscillates. But because we've got an electric charge which is now moving, you'll remember that that causes a magnetic field. You don't need to know the specifics of all of this that I'm telling you. What I do want you to remember is that a moving electric charge will cause this oscillating electric field and an oscillating magnetic field. That's the summation that I want you to remember. as that charge is moving, so if we move that charge up and down in SHM, in simple harmonic motion, at the top, it's not moving for a moment, at the bottom, it's not moving for a moment, and as it goes through the middle, it's moving the most. And where it's moving the most, that's going to be creating the strongest magnetic field. And so we're going to get a magnetic field that also oscillates just like we had with the electric field. So as you oscillate this charge up and down, you're creating electric and magnetic fields that are both oscillating as well. And that's what photons are. That's what light waves are. Light waves are these oscillations in the electric and magnetic fields. That's it. That's all they are. And so when you send a particle oscillating, it sends energy off through space, and that energy is in the form of an electromagnetic wave. Electromagnetic because it is oscillations in both the electric and magnetic fields. Right? That's it. Electric and magnetic fields oscillating, therefore electromagnetic wave. The words light and photon are kind of interchangeable. We do want to be careful with our language. So light and electromagnetic wave mean the exact same thing. So a light, if you're talking about light, you are talking about some kind of electromagnetic wave. Photon is the individual little wave packets. So remember I said you could sort of shake your rope up and down a half dozen times and send this little set of pulses down the rope. That's kind of like what a photon's doing. So the thing might not be the photon or, proton or whatever is causing the photon, might not be oscillating constantly. It might just oscillate a little bit. And so that'll again send a little photon, a little packet of waves along the electromagnetic fields. And that's what photons are. So these little sets that result from these little short oscillations of charges. But for our purposes, we treat photons as little particles when we get into particle physics, which we're not going to get into, unfortunately. It's a very interesting area, but we don't have the time for it in this course. So we just talk about photons as little packets of energy, and we talk about light and electromagnetic wave as being just the same thing, light and waves. In everyday language, though, just to confuse things, when we say light, we often just mean visible light. In everyday language, if we talk about visible light, we're not going to specify visible. We'll just say light, and we know that other people know that we mean the colors we can see. We don't talk about the microwaves coming out of a microwave oven as light, even though they are. We don't talk about that in that same way we talk about them as microwaves. So we sort of have this there's slight different use of terminology in everyday versus science. And so again, it's just one of these areas that you want to slow down and be careful, make sure you understand the different terms, and make sure that for any scenario, any discussion, any question, that you are clear on what terms you are using and what they all mean. The speed of light, how quickly does that little photon, those wave parcels, travel through the electromagnetic fields? They travel at the same speed all the time. Everywhere in the universe, there it is 299,792,458 meters per second. That's meters per second, right? That many. So around about 300 million meters every second. So that's the speed of light, and it is true anywhere in the universe where there is a vacuum. We'll talk a little bit more about that when we get to the concept of light slowing down as it travels through a medium shortly. The frequency of an EM wave is the same as the frequency for other waves. It's the number of oscillations that happen every second. In this case, there are two fields doing the oscillating, the electric field and the magnetic field, rather than just matter. But they always oscillate together. They always oscillate at the same frequency. So we can just refer to one frequency when we talk about an EM wave. If the vibration has more energy, then that means it's going to oscillate a bit more quickly, and we're going to get higher frequency. So higher frequency is higher energy. Lower energy is lower frequency. So the frequencies change. Remember, the speed is always the same, but the frequencies change. Because the speed's always constant, if the frequency changes, then the wavelength must be changing as well. So a higher frequency will have a lower wavelength, right? A shorter wavelength. Saying lower is confusing. A shorter wavelength. A lower frequency will have a longer wavelength. So because that speed of light is constant, we can refer to either the frequency or the wavelength of light, and we know exactly the wave properties. In the other kinds of waves, when we looked at waves on water or sound waves, then because the speed can change, so the speed of sound in water versus air versus different materials, or even just in different temperature air, the speed of sound changes. So you would need to know both the speed and the frequency to get the wavelength. Whereas for light, it's always just going to be the same speed regardless. Just about always. We'll talk about that a bit more soon. So if we have C equals F lambda, an increase in frequency means a decrease in wavelength. As I said already, low energy, longer wavelength, high energy, shorter wavelength. And again, makes sense. If they're oscillating really quickly, they're not going to travel as far between oscillations, and that's the definition of your wavelength. The Planck-Einstein equation is a nice one. I'm not going to explain any of the background of it or understand where it comes from or anything. I just want you to learn it, to know this equation. This is the energy of a single photon. A single photon of a specific frequency always has the exact same amount of energy, and that is h times f. H being Planck's constant, 6.6 times 10 to the negative 34 meters squared kilogram per second. That is Planck constant. And f being the frequency of the photon, you just multiply them together, and that's how much energy is in that packet. That's it. It's always the same. If you have a photon of some specific frequency of light and another photon of the same frequency, they are both going to have exactly the same amount of energy in them, and it's going to be given by HF. When we talk about electromagnetic waves, as I've already hinted at, we have different regions. We have visible light, we have ultraviolet, infrared, and so on. And these different regions have different names based on what we do with them. So as a quick example, or not example, a list, lowest frequency of visible light is called red, and the highest frequency of visible light is called violet, and we get other colors in between. Infrared, infra meaning below, we've met that when we talked about infrasonic, infra being below, so infrared is below red. Ultraviolet, again, ultra being above, so ultraviolet greater than violet, so higher frequencies, higher energy than violet light. As we get more energetic than that ultraviolet, we go up through X-rays and then through gamma rays. Gamma rays are the most energetic photons. As we get less energetic, so we go down below infrared. So below infrared, we get down through microwaves, and yes, that's the kind of microwaves that are in your microwave oven at home, and then down through radio waves, which are the kinds of waves we listen to when we listen to radio. All of those different types of waves are all electromagnetic waves. They are all fundamentally the same thing. And the boundaries are not real boundaries. There's no strict cutoff. You can't look at a photon and say, oh, that's a visible one, that's an ultraviolet one, that's a radio wave. You can't look at them and do that. What we have is regions that we sort of describe in general ways based on our use for those waves. Right, that's it. It's just the uses of the waves. Radio waves could be used for other things. We use them for radio, so we call them radio waves. Visible light waves are called visible light because they're the ones our eyes can detect, but other animals can actually detect other regions of electromagnetic spectrum that we don't call visible light, even though they're visible to those other kinds of animals. So the names for these categories, for these regions, are based purely on our use of those waves. Right? That's it. It's just an arbitrary name that we've given it based on what we do with it. But as I mentioned, fundamentally, they are all the same thing. They are all oscillations of the electric and magnetic fields at different frequencies. That's it. So a low energy, low frequency radio wave is fundamentally the same thing as a high energy gamma ray, right? And as visible light rays and every other kind of electromagnetic wave. Visible light is the easiest place to start because it's the one we're familiar with. We know that there's a bunch of different colors. We've seen it with rainbows, Roy G. Biv, if you've learned those, red, orange, yellow, green, blue, indigo, violet. And the image below on the slide, at the bottom of the slide, is that spectrum. It shows all the colors that we can see. But again, just like with sound, humans can hear slightly different ranges, but usually have a pretty similar overall range. The same thing is true for visible light. Most humans can see in the range of 400 terahertz, which is a wavelength of 750 nanometers, up to around 790 terahertz, which is a wavelength of around 380 nanometers. And that's the violet end, the 400 terahertz being the red end. So most humans can see pretty much the same range. We're pretty good at all having a very similar range, but there will be some photons right on the borders that some people will detect and others won't. But it's not a huge issue, especially as you'll see when we talk about colors in the next section. So that's the visible light spectrum, right? It's a pretty small region, 400 terahertz to 790 terahertz. They're big numbers, but it's a fairly small region, as we will see, because the overall spectrum goes from waves that are longer than a kilometer to waves that are shorter than the width of a proton or in a nuclei, right? They're tiny, tiny waves when we get down to gamma ray. So looking at visible light in the center, you can see the little rainbow that they've put in there in the visible light spectrum. The wavelength being around the 10 to the negative 6, the frequency being around 10 to the positive 14, and that is about the size of bacteria. So that bottom row of this diagram includes sort of items, real world objects that are around the same scale. So bacteria are around the same scale as visible light wavelengths. As we get to the lower energy, the lower frequency, the higher wavelength, longer wavelength, and bigger items, we get to infrared. So infrared is that region below red, and you'll see that that region is, it's quite big on our diagram. It's the visible light is a fairly small little sliver of the electromagnetic spectrum that our eyes can see. As you get lower, you get down into infrared, and that's getting down up to the size of a pinpoint, moving into microwaves that are around about a few centimeters in wavelength, so around the size of bees or insects. But microwaves can be longer. The ones in your microwave oven are a couple of centimeters, but they can be a little bit longer. And as you move into radio waves, they're the longest kind of electromagnetic waves, and they can be as big as football fields or mountains. They can be up to kilometers in length. So they can be very large indeed. The other side of the spectrum, getting higher energy than visible light, so shorter wavelength, we move up to ultraviolet. The people who made this diagram, which I happily stole off the internet, have missed the T on ultraviolet, and I haven't got around to adding it in. But ultraviolet light waves are around the size of molecules. As we get more energetic into X-rays, we're getting down to the size of atoms, and as we're getting right into gamma rays, the most energetic, the shortest wavelengths, the highest frequencies, we're right down at the size of atomic nuclei. The gamma rays are coming out of the nucleus, so it makes sense that their wavelengths are going to be the size of the nuclei. So that's the electromagnetic spectrum, that whole big range. As I said, there is no hard boundaries. You can't pinpoint a specific frequency and say more than this is a microwave, less than that is a microwave and more is a infrared. You can't do that. There are no boundaries like that. As I said, it's based on our use. So we'll look at a wave that's maybe a couple of centimeters and go, well, if humans were going to harness that, we'd use it for a microwave. So we'll call it a microwave electromagnetic wave. That's what electromagnetic waves are. We're now going to talk about what happens when these photons meet matter. So they can travel through a vacuum. They don't need matter, but what happens when there is some matter? When a photon meets the matter, different things can happen. It depends on the properties of the light wave, so the frequency and thus the energy in the photon, but also on the properties of the matter that the photon is hitting. So if it hits one type of matter, it might do one thing. If it's a different type, it might do something else. Because the photon is essentially just a little packet of energy, there are really only a few things that can happen. The atom absorbs the energy, the photon bounces off the matter, so the energy doesn't get absorbed, or the photon travels through the matter, so the energy essentially passes through the matter and doesn't really care, or not that it doesn't care, but it still goes through the matter as if the matter wasn't there, but it might be affected in other little ways. When the photon bounces off the matter, so the energy is reflected, then that's just reflection of a wave, as we already saw with sound and other types of wave. That's exactly the same phenomenon. It's just reflection of a wave. It's very common with visible photons in metals, again, because metals have free electrons. We've seen those free electrons are responsible for quite a few different phenomena, including electrical and thermal conductivity, and they are again responsible for the reflection of visible light. So it's the free electrons that help visible light bounce off the surface of a metal. And indeed, if we polish it up and get it really smooth, so we have a nice smooth surface, and we can get mirrors, which are created by putting a coating on the back of glass for a home standard mirror, or just by polishing a piece of metal until it's really smooth, like you can see with this sculpture. I forget where in America that is, I'm afraid. So photons bouncing off metal is just a reflection. Photons can also be absorbed by an atom. Photon photons of different wavelengths and different frequencies will get absorbed by different atoms with different readiness, like different ease. Same as we saw for the idea of thermal radiation absorption and reflection and emission. Yeah, emission, getting off topic a little bit there actually, sorry. But we've got absorption and reflection. So a photon hits a surface, might get reflected, it might get absorbed. Same idea here. And because the absorption is that thermal physics phenomena we're talking about, we often actually call infrared light waves heat waves, because they are very commonly absorbed by matter. But it's the same phenomena we've already talked about. Again, all this overlapping, and that's sort of part of the point of this course, to try and highlight some of these overlaps. So here what we've got now is the idea of a photon, which we've met as a wave, an electromagnetic wave, that ties together our electric fields, our magnetic fields, so that whole electromagnetic region ties together our study of waves. And now we're saying that infrared waves are absorbed by materials and make them hotter, and that's tying in our thermal physics as well. And obviously throughout all of this, we've got energy conservation, because energy is the thing that is being transported by the wave. So this idea of a heat lamp ties together so many different fields of physics. It's actually a really interesting exercise to just sit there and look at how it corresponds with all these other different areas of physics. And of course, if you want to get into the manufacture of the lamp, then you're going to have to look at electric circuits and how the power works there, as well as the physical structure, so the strength and the creation of the objects itself. So fascinating topic, but only one slide here from me. The last one that we said is that the photon can travel through material, through it. So not absorbed by it. The energy doesn't get absorbed and turned into heat, but the photon travels through the material. This is called transmission. Slightly different from what we talked about when we talked about, for example, a sound wave being transmitted. A sound wave being transmitted was the idea of the wave itself being changed in form from the oscillation of one medium into the oscillation of another medium. So it might be the air oscillating, and then that air might hit a wall and the wall might start oscillating. So the energy is being transmitted, but the thing that's vibrating is changing as part of that transmission. The important thing to realize here with a photon being transmitted through a medium is that even though the energy is going from being outside the medium to being inside the medium, it's still an electromagnetic wave. It is still the oscillation of the electric and magnetic fields. But otherwise, same concept. The energy is traveling outside the medium, and then it's traveling inside the medium, and it's still traveling as a wave. And this is most common for us to observe in the form of glass or clear plastic. Right? We can see through glass, we can see through clear plastic. That's because visible light photons travel through those materials. Right? They travel just straight through them. When they do go through those other mediums, they actually travel a bit slower than light in a vacuum. So I said the speed of light is a constant, it's c, it's 300 million meters per second. Everywhere where there's a vacuum, as soon as you put matter in the way and the photon has to travel through the matter, it actually slows down. Right? It does slow down, and that's refraction, which we've already met as well. The idea of the wave traveling at a different speed because it's in a different medium. So we've already talked about refraction, and we're going to see how that works with light and photons as well. The textbook gives you a poor explanation for why light is slower in a medium. It's just flat out incorrect, right? They talk about atoms absorbing photons and re-emitting them, and that's not correct at all. That's a different type of phenomenon. That's the absorption of the energy and the conversion into thermal energy. Right? So that's a different issue entirely. They did it because they're trying to be very simplified, but I feel that it's just confusing when you talk about the same thing happening two different ways, and one of them magically results in transmission and one magically results in absorption. So if you have read that section of the textbook, please forget it. Why does it actually go slower? This material is not examinable. You do not need to know this, but I include it because it is, again, interesting, and it's also completely possible for you to understand it and realize why it works. So remember that light is an electromagnetic wave. That means the electric and magnetic fields are both oscillating. That's what the photon actually is. Remember also that matter is full of electrons orbiting atoms. So the electrons orbiting atoms are negatively charged. They will experience a force due to this electromagnetic wave. if the electric and magnetic fields are oscillating, that electron is going to be experiencing these oscillating forces on it, because as the electric field changes, the force on the electron is going to change. So you're going to get this oscillating force on the electron. That means the electron is oscillating. And the oscillating force is going to cause the electron to oscillate, but an oscillating electron, we already saw, causes an electromagnetic wave. Right? And so now we've got two different electromagnetic waves in the same space, and that's just superposition, that's interference. And so the electron wave and the original wave interfere with each other, and the new wave has a slower speed. Right? That's all that's causing this change in speed of a material, of light through a material. As I said, not examinable, but certainly accessible for you at this stage in the course. What kind of speeds do we get? Well, the speed of light in a vacuum, we already said, was 300 million meters a second. In our atmosphere, so in the air, it is technically slower. Right? It is technically slower, but it's so close that for just about everything we do, we can treat it as being at sea. It's very, very small fraction of a percent slower than sea. So for our precision levels, we certainly don't care about that. You have to get very high precision before that change in speed becomes relevant. In water, though, it slows down significantly. It gets to 0.75 C, and in glass, it gets down to about 2/3 of C, although it varies depending on the specific type of glass, what it's made of, and the properties of it. If you get all the way down to diamond, it slows down to less than half the speed of light. Now, that's still really high because we started at 300 million meters a second, but now it's traveling at only 40% of that. So it's still very high, but less. I don't know exactly what that would be, and you can calculate it if you're interested. Opaque materials, so we've got the idea of transparent materials. Transparent lets light through. Opaque means no light can get through, not transparent. That's all opaque means. Most materials around us are opaque. Most materials we can't see through. Light still hits them. They still absorb some of it and reflect a bunch of it. How much they absorb and reflect depends on the properties of the material again, but they don't transmit light through. So if you have a light bulb and it's shining on a wall, the point of a wall is that it doesn't let light through. So light is not transmitted. You get light being reflected, you can get light being absorbed, but you don't get any light transmitted through the wall. If visible light was transmitted through the wall, then you'd see through the wall. Right? I should specify this is talking about visible light at the moment. Opaque is a definition of visibility, and so it's talking about visible light specifically here. Walls, of course, will transmit other types of light. They'll transmit radio waves. That's why you can hear a radio when you're inside a house, even though the radio wave is coming from outside. In terms of the visible light, they do absorb some of it, and that is turned into kinetic energy, and things get slightly warmer. And that's just going back to our thermal radiation, right? The idea that we get visible light from the sun, it heats things up. Let's talk about rays and shadows. We've already met the idea of a light ray, well, of a wave ray, and now we're talking about light rays specifically. And it's exactly the same as we talked about for wave rays in general. It's just the direction that the energy is being transmitted by the wave. For a light source, it's just isotropic. It goes out in every possible direction. The sun is isotropic. It sends photons out in every direction and equal amounts in every direction. That's isotropic. So no matter where you are around the sun, you'll be getting the same amount of photons as if you moved around this side or around this side. Excuse me. So that's what light rays are, exactly the same as we saw for rays before. What about wave fronts for light? Wavelengths for light are very small, right, for visible light. Remember, the wavelengths for visible light are 750 nanometers, right? That's well, that's for red light. It varies. There's a range, obviously. 750 nanometers. If you were going to draw a diagram of light and you wanted to draw the wavefronts on it, you would need to make the scale big enough that you could draw one wavelength, one wavefront every 750 nanometers. That would mean if you were doing a diagram that was only covering 1 millimeter of this red light, 1 millimeter, right? Tiny, tiny distance, 1 millimeter, you would have to draw 1,333 wavefronts. And so that's a ridiculously big and complex diagram. So the point is we don't bother with wavefronts for visible light for any higher frequency. You could potentially get into wavefronts if you move down into looking at microwaves or radio waves, but because there's so much of the spectrum that we can't use wavefronts for, it's pretty standard to only ever use rays for any kind of light, but especially for visible light. And as you move into the high energy lights, we definitely only stick with rays. Remember that the sun sends circular waves out, right? Circular waves appear straight by the time they get very far away. This is what we talked about with the idea in, I think it was the previous lesson, that we talked about a source sending circular waves out, and if you're far enough away, they'll appear to just be parallel wave fronts approaching you. Same thing with the rays being essentially parallel, right? They'll appear to be parallel, even though they technically come from a point, so they're very slightly off parallel. They'll appear to be parallel if you're far enough away. And that's what the sunlight is like. We are so far away from the sun that the light rays, by the time they reach us, are for all purposes parallel. They are practically parallel. They are so close to parallel, you can't even measure the difference. It's how close to parallel they are. We don't have the technology to measure that difference, how far off parallel they are. So that is, or at least last I checked, we didn't. Maybe there's been some advancements, but that is how close to parallel the sun's rays are, which is great for us because it sets up really nice experiments where we have incoming parallel light rays from the sun that we know are parallel, right, to all, as I said, all significant figures that we'd ever want to work with. If you've got parallel light rays coming in, and you put an object in the way of them, then where the rays do not hit the wall or the surface behind the object is called a shadow. We're all familiar with shadows. This shouldn't be new information for you. It's the same definition in English or in general language as it is in scientific language. A shadow is just the area where the light doesn't hit. If the light comes from a close source rather than a large faraway source, in the previous slide, I'll go back a second, this is a large faraway source, which when we talk about a large faraway source, we're generally talking about something like the sun, so that the light rays are practically parallel. That's the point of a large faraway source. The light rays are practically parallel. If we've got a close, small source, then all the light rays will appear to be coming from a point. We'll still get a shadow. Right, we'll still get a shadow, but now the shadow will be a different size depending on where the object is. And that previous one, that shadow is the same size as the object, right? It's the same size as the object because it's just parallel straight down where the edge is, that's where the shadow is. But in this one, depending on how close you move that object to the surface or to the light source, that shadow will change size. So you'll get a different size shadow. But the idea of the shadow is still exactly the same. It's where the light rays aren't hitting the surface, that's where the shadow is. Right? And it'll still be sharp. You'll still get this very distinct border between there being a shadow and there not being a shadow. It's dark here and it's not dark here. This very distinct, sharp boundary. That region of shadow, the technical scientific name for it is umbra, U-M-B-R-A, umbra. If the shadow is sharp, the entire thing is the umbra. But we know that shadows aren't always sharp. Sometimes we get blurry shadows. What's going on with those? If we have two light sources, then what we get is these regions on the wall or surface where both the lights are hitting the wall, or where just one of them is hitting the wall, or where neither of them are hitting the wall. Hopefully, if you spend a bit of time looking at this diagram here, you can understand that. Right? The green and red lights are both just white lights. They're just standard lights. I've just colored them green and red for illustrative purposes. But you can see that the green light source, right, that can hit the wall up the top. It can hit it during that slightly grayer bit, and not at all during the black bit, not at all during that second grayer bit, and then it can hit it again down the bottom where the lightest bit of the wall is. The red light source does the opposite. It can hit that top one where it's the lightest, but it doesn't hit that second grey one. It doesn't hit the black area, but it does hit the next sort of greyish green bit and the bottom as well. So what we're getting is this idea of the brightest bit of the wall being where both the lights are hitting it, the sort of intermediate step where we've got one of the lights hitting it but not the other. So it won't be a shadow, it won't be complete shadow, it'll be a partial shadow because it's not as dark as the shadow, but it's also not as bright as where both the light sources are hitting the wall. And that's called a penumbra. Pen meaning next to, the same origin as the word penultimate, if you're familiar with that. And that penumbra is basically saying partial shadow. That's all it means. Umbra is full shadow, so there's no light source hitting it. Penumbra is partial shadow. There is some light source hitting it, but not all of the available light sources in that space. Sorry, there was just a thing up by my camera. So that's what umbra and penumbra mean. But we also have blurry shadows rather than just sort of stepwise shadows. So in that previous example, we stepped from full light to half light to no light, and then back to half light, back to full light. We also get blurry shadows where it just sort of gradually fades from being full light to being no light. And that happens when you have a light source that's big, that's not just a little point. So in that previous one, I go back a moment, we've got two light sources, but they're both just tiny little point sources. And a tiny little point light source will create a sharp edge. Right? And if you've got two light sources, like in this diagram, you get two sharp edges, and so you get these sort of overlapping shadows. And so that's why you get the step from both lights to only one light to no light. When you've got a big long light source, like a fluorescent light in a room, if you're in a classroom or something, you'll see those sorts of fluorescent lights. I could probably actually just tilt up and show you one of them. You can see in the reflection there, those long sort of light sources like that. Then what they will do is they will cause a blurry shadow. The way to think about that is if you imagine, instead of being one long light source, imagine that light source being broken up into a whole bunch of tiny little bits of light source. Maybe I'll do this on the document camera just to hopefully be really clear about it. So on our really long light source, and we've got some kind of object in the way, and then we've got a wall over here. And so we want to think about this light source, instead of being one long light source, let's think about it as being a whole bunch of separate little light sources. So each of these little segments is one light source. And so this is what would happen if you went and lined up, say, 20 little LED lights. Think about the light from this first one. This first one, it's just like we saw in the previous section, right? This light can hit here, so it can hit all of this. It can't hit this bit here, but it can hit again down here. So it can hit there. So that light source can hit all of that and all of that. This bottom one here, same idea. It can hit all of that. It can hit up there, but it can't hit this region here. Right? So this bit here is going to be missing that last light bulb. This bit here is going to be missing that first light bulb. But this bit up the top, this has all of the lights, and this one down here has all of the lights. Because if that top one can reach it, right, then clearly all these other ones can. If you choose any other one, same thing. It's going to be hitting here. It's going to be hitting up here, but it's not going to hit there. And so you can work through, and what you'll see is that if you're above that point, all of these light sources can hit it. All of these can reach that. They're not impeded by the object. If you're below this bit, all of the light sources can reach this bit. But if you're anywhere in between, then the amount of light sources you can see from that point on the wall will determine how bright you are. So let's take an example. Let's choose one here. Let's look at this spot. If you look here and you look at the light source, then you can only see that many of the lights. You can only see, say, what's that, 2/3? You can see 2/3 of all the lights. That means this is going to be 2/3 of the brightness. By the time you get to this very center spot, you can't see any of the light. You can't see any because there's none down here and there's none up there. You can't see any, so you're going to be 0 brightness. So you'll have no brightness at all right in the middle, so you'll get this very tiny full umbra. And as you move out, the more light you can see at that spot on the wall, the brighter it's going to be, up until you get to here, where you can now see all of it and you will get full brightness. So that's why you get blurry shadows. And you can probably see, if I use this pen as an example, with the lights overhead that you just saw, you get very blurry shadows here, right? These are very blurry because those light sources are long. You can also see that there's two different shadows because I've actually got 3 lights, but one of them's a bit further away, so you're not seeing it as well. You're getting a couple of different shadows, and they're blurry because they are large light sources. So hopefully that'll make sense about the shadows. So we do hope that you understand the shadows. We're not going to build on that knowledge much any more than that, other than hopefully understanding the different types of shadows. To provide an example, there is a photograph. I can't remember if I stole this out of the textbook or online somewhere, but it's just a photo of an orange. The left one, we've got a large faraway light source, so the sun, or possibly a small, close, very small, close light source. Either one would produce a sharp shadow. The photo on the right, though, is a large nearby light source, so a big light, and that's causing that blurry shadow. It fades in from full light to low light. So those are the different types of shadows. Just basically, is it sharp or is it blurry? Do you have one light source or multiple, and things like that. Next part is talking about the greenhouse effect. I think this is the last part of the lesson. Greenhouse effect. So we've already talked about thermal radiation, and as you're seeing in this lesson, there's a lot of overlap with electromagnetic radiation and thermal radiation, because thermal radiation is a type of light wave. It's just the photons being emitted by material. When studying heat transfer, we said that everything radiates energy, and how much it radiates is determined by how much thermal energy it has. The hotter it is, the more energy it will give off. If it's trying to give off more energy, it's going to be emitting different frequencies than something that's low and trying to give off less energy. And so the range of frequencies that an object gives off is determined by its temperature. And that is the frequencies that it will give off are going to be higher for a hot thing and lower for a cold thing. The exact temperature it is will determine its peak frequency. So there will be some frequency that it gives most of compared to all the others. It still gives a big, huge range of different frequencies, but there'll be a frequency which it gives most of, and less either side. The graph of that frequency versus how much of it gives off, which here is called intensity. So intensity in this graph just means how many photons, essentially. How many photons it gives off for each different frequency is called a radiation curve. And what you can see, we've got different colored lines here. That tiny little one with a little bump that's down around 150 terahertz, that's for something at 3000 Kelvin, right? 3000 Kelvin. So we're still at very high temperatures. But the peak frequency there is quite low. It gets high as you get up to 4,000, 5,000, and so on, all the way up to 8,000, being around 500 terahertz. So the different temperatures will give off different peak frequencies, and as you can see from this picture, it gives off just overall more photons as well because it's much hotter, and that makes perfect sense with what we talked about. The sun is, not surprisingly, very hot. It's a big ball of burning gas, essentially, so it's going to be very hot. It has a peak frequency of radiation that it gives off of around about 6 times 10 to the 14 hertz. Right? 6 times 10 to the 14 hertz. And that's right in the middle of the visible region of the electromagnetic spectrum. And this is not a coincidence. The reason we can see those visible frequencies is because they're the ones the sun gives off the most. Because they are the ones the sun gives off the most and always has given off the most as life evolved, it used the most common frequencies in order to detect the environment around it. It made sense for it to be able to see the frequencies that were most present. And so that's why eyes evolved to detect those frequencies. So I mentioned earlier that other animals can see different frequencies. They always see these visible ones in the middle, just some of them can see a little bit slightly wider range in some areas. Right? But all life can see, if it has eyes, it can see these visible region waves because that's the one the sun gives off the most. The Earth also gives off thermal radiation, but the Earth is a lot lower than the sun in terms of its temperature. And so the radiation curve of the Earth has a much lower frequency peak. The frequency peak for Earth's radiation is around about 2.5 times 10 to the 12 hertz, which is in the infrared region. Remember that those are the ones we called heat rays, right? Heat waves. The Earth is giving off infrared light. The sun is sending us visible light. And that's important because glass has been made to be transparent to visible light, but it's opaque to infrared light. Remember, opaque means it won't transmit. I said we use that for visual terms. For visual light, normally But opaque will mean, if you're talking about a specific light wavelength, it means the same thing for that wavelength. So for infrared light, being opaque to infrared just means infrared can't be transmitted through it. So glass will let in visible light. That visible light will get absorbed by stuff, by things, whether it's the inside of a car or whether it's a greenhouse with plants in it. The things inside the glass area will absorb that energy, but because they are lower temperature, they give off different frequencies than they absorbed, and they give off infrared. Right? A lot of infrared is given off by things being warm to the sort of level we have on Earth. Those infrared light waves cannot leave through the glass again. So that energy becomes trapped. So it gets in through the glass because it's a light wave and that can travel through the glass. But then once it's absorbed by objects and re-emitted as thermal waves, as heat waves, as infrared photons, it cannot leave through the glass. So it's trapped inside that area. So whether it's a glass house or a car on a sunny day, you'll know they get very hot. That's exactly why. The same reason greenhouses work. It will increase the average temperature by catching that sunlight and not letting it leave again. The greenhouse effect, though, also applies to the Earth as a whole. For the Earth as a whole, the atmosphere is acting kind of like that glass. The atmosphere lets in visible light. Right? Visible light can travel through the atmosphere. It can travel through all the nitrogen gas and stuff that makes up our atmosphere. And that's obviously why we can see light, because it travels through the atmosphere. But it's not as good at transmitting infrared waves, just like the glass. Right? It's slightly different, but it's the same process. It's good at reflecting that infrared light back towards Earth and letting very little escape Earth. But it's also good at letting in all the visible light and not reflecting much back out into the solar system. So that means that the Earth as a whole is doing the exact same thing as the greenhouse. Right? It's doing the exact same thing. It's letting in the visible light because the atmosphere is transparent to visible light, but it's not letting the infrared light leave Earth because the atmosphere is not transparent, not fully transparent to infrared light. It's partially transparent, so some infrared light can get through, but not much. If there was no greenhouse effect, if the visible light could come in and the infrared light could all leave, if it was just free to leave and the energy could leave Earth again, then the Earth wouldn't be trapping any of the energy. We wouldn't be able to build up that energy and get warmer, which is what the Earth does. Instead, the Earth would just be a solid frozen mass. It would just be a big frozen lump. We wouldn't have any life or anything. It would only probably be a few Kelvin. The exact temperature varies. It's hard to predict based on unknown information, but it would be very cold because we wouldn't be able to keep any of that energy from the sunlight. That's if there was no greenhouse effect. On the other hand, if we had too much greenhouse effect, then we would get too much energy. The temperature would get too hot. All of the ice on Earth would melt, all the seas would evaporate, and we'd end up with a dry, barren landscape with a really humid atmosphere full of water molecules. And so again, not very good. If there's too much greenhouse, that's no good either. Global warming is that process happening at a slower scale, right? It's not instantly huge greenhouse effect and get all the energy, but it's happening more slowly. Certain particles in our atmosphere are better at blocking that infrared radiation. They're better at making sure it stays on Earth. And if we put more of those particles into our atmosphere, then we will keep more of that energy on Earth. We will let less off into the universe. And that will increase the temperature here on Earth. Water vapor is the primary component that reflects infrared radiation back to Earth, but carbon dioxide comes in second. And if we increase the amount of CO2, it will increase the average amount of energy on Earth, the average temperature on Earth, and indeed that's exactly what is going on at the moment. At this point, I'll just add another comment on climate change. This slide again is not examinable, but it's a common question that I get, and so I just like to mention it. Scientists used to call climate change global warming, and now we call it climate change. And there are skeptics that will argue that we renamed it because we don't really know what's going on, and if we don't know what's going on, then why should we listen to scientists about it at all? In reality, it's because a higher average temperature system means there's more energy in the system, more energy that's moving around through our system, and that makes it more volatile. Think about a pot of water. When it's cold, it's pretty calm, it's pretty stationary. As you heat it up and you start to boil it, it gets more violent, and you get these big changes. You get hot pockets that will suddenly turn into a bubble and boil off. So you get more volatile. So it's not quite the same thing, but it's a similar idea that as the Earth's atmosphere gets more energy overall, then it will start to get these sort of volatile spots, and we will get more fluctuation, more extremes, not just hot extremes, but also cold extremes. So a record-breaking cold front is part of global warming. It's part of climate change. It's not counter evidence, as some people like to claim. So that's just a little comment. As I said, not examinable, but a lot of people are interested in that side of it. So that's the end of this lesson, which, as I said, was the goal was to introduce electromagnetic waves and understand what we mean by light, what it is, but we also threw in there a bit of discussion about shadows and about the greenhouse effect and thermal radiation.